There was better notation, as it turns out. So, let's see. Today we're supposed to do gradient again. Okay, and I'm going to give you better notation because the notation I was using yesterday was horrible. So, I'm going to say f in the u direction, evaluated at a point A, B, C, is going to be a vector, right? Wait.
I gotta go sit somewhere else. It's way too sunny right here.
It's going to be a vector?
What
should this thing be?
It's a dot product.
Yeah, this should be the result of a dot product, right? This should be the gradient of f dot producted with a unit vector pointing in the u direction, right? So I need to make sure this thing's a unit vector. And then I should remember to evaluate the gradient of f where?
At your point.
At my point.
I can't even word anymore. It'd be too distracting.
Okay, cool. Everybody good with this? And then we should remember that the gradient vector, right, is what? How do I make a gradient vector?
fx, I...
Okay, so it's fx in the I direction,
Fy,
J
plus
plus
fy in the j direction.
plus FZ. If we're A,
Yeah,
B,
and then
C.
if there were more things, right,
In
I
this
just
case,
keep
yeah.
adding.
Yeah.
So here's the content of section 14.5.
one more dimension.
fz times
Do
Okay.
they really need to break this up as much as they do?
I don't really think so. There is something pretty cool in this section, which I actually learned today. So we will learn something new today.
Cool.
Let me give you some properties on this that we could probably guess from yesterday. So, what are gradient properties that might be useful? What did we learn yesterday? How about when's a dot product biggest?
oh, cosine of 0.
Yeah, when the angle between two things is 0, right? So this gradient, right, points where? Yeah, uphill. Let's call it uphill. Although that's going to make a little less sense, right, in the three-dimensional context.
Maybe always greater than 0.
So what I mean is points towards greatest increase, right?
So higher function values.
Yeah.
And it won't ever be negative, right?
So this points towards the maximum change. What do you mean it won't be negative?
Well, if it's always pointing uphill, then it will never be negative.
What's that? Yeah, so the opposite of the gradient would point maximally downhill, right?
But unless you were to find the opposite of the gradient, the regular standard gradient would always be positive.
So this is going to point towards positive change, right?
Okay.
Positive change doesn't necessarily mean that you're ever positive.
Positive. I think we're thinking of different things. 'Cause
Right?
that's what I meant, what you just said. Positive change.
Yeah. Okay.
Like it
Okay.
has
Cool.
a positive slope, but it's not like positive numbers.
Right, that's not what
Yeah.
I meant. I meant
Yeah, yeah.
positive change. It's always going to be the derivative or whatever will always be greater than 0. The
Will always be
slope of it will
greater than or
always
equal to 0, right?
be- Right.
Yeah, because when you're
Yeah,
at a
it's-
peak, the gradient's
It's
zero.
kind of impossible for me to make an area that's globally downhill on a surface, right? Okay, see that? Unless it's the top of something, right? In which case the gradient is going to be
0.
0. Cool? Alright, so that's one of the things we should know is that the gradient points uphill, or really towards maximum change, right? Let's see, what else is there? Well,
If you're on a peak.
okay, that's good. So, at peaks or valleys or saddles, right?
Yeah.
What would you call
Points of
those
interest.
things?
Critical points.
Critical points might be a good
Points of
idea,
interest.
right?
Interesting points.
And I'm calling this loosely critical points, right? because what I mean by a critical point is going to need a slightly better definition. But at critical points, gradient of f should be 0. Does this equation as written make sense? No. Liar. What's the gradient of f?
The grade.
Yeah, it should be a vector, right?
Okay, so it's 0 vector.
That better be the 0 vector.
In this context, is there anything special that happens at the inflection points?
I don't even know what an inflection point means.
Isn't
here.
that the change of sign and slope? Isn't it?
I thought it was the change of concavity.
Yeah, so
Oh,
it's
it is,
a
okay.
change in concavity, and concavity makes sense in one dimension, but in two it gets really weird, because I can have points that are kind of simultaneously, right, like the top of a saddle. In one direction it's concave down, and in another direction it might be concave up.
Mm-hmm.
And then I can kind of turn, right, and things get really strange. Cool? Like if you're looking straight out along the level curve, the concavity is going to be 0, right?
Yeah.
And every point on the surface is going to be on some level curve, assuming there's something reasonable happening.
I
Cool.
think the change in slope thing is the critical point. Because you usually don't change slope unless you're coming to a min or a max. Or a
I think
solid.
it borders
Changing the
between
sign of
inflections.
slope is a critical point.
Yeah.
Changing the sign of the derivative of slope is an inflection point. Let's see, what else did I want? Okay. Let me see if this makes sense. The gradient of f is perpendicular to, what would a good,
Perpendicular to the contour line.
what? Oh yeah, right? It's perpendicular to the contour line. Why? Why would that make sense?
Because contour lines are when you're setting z constant. So
Yeah, because it's the steep part. The steep part's going to be perpendicular to the flat part. Duh. Right? So this is perpendicular to level surfaces. And this is really where the cool thing comes in today. It's also perpendicular to contour lines. Your book wants me to warn you, and I feel like I probably ought to, that it will only look perpendicular as long as the units are the same on both axes. If the units are different on both axes, then this thing might not look perpendicular, and it's because you really need to kind of adjust your glasses, right? All right, how about this thing? What's the magnitude of the gradient of f? What's that going to tell you about? Yeah, that's going to tell you the length of the gradient vector, right? But what is that information going to contain?
Slope.
Yeah, that's going to contain something about the slope, right? So, I'm just going to write tells us about steepness. What do I mean by tells us about steepness? I mean if the gradient vector is bigger, the ground there is steeper. Right? Does that
Like
make
the whole
sense?
rise over run.
Yeah, this is kind of the idea of rise over run, right? You guys see that? Okay, so these are things I want you to know about the gradient vectors, and I want you to know how to calculate them. Cool? Check.